All right, welcome everyone. So a week from today is our first exam. This is a friendly reminder, right? Your homework is due this Friday. I will have the homework posted after it's due, but I obviously won't be getting your graded homework back to you before Monday. They don't see you before Monday, right? So, right, I suggest making a copy or something like that for your homework if you want to study your answers and compare the answers and things of that nature. Right, so today we're going to talk about kind of exact and inexact differentials, talk about changes in internal energy, and then on Wednesday we'll talk about changes in enthalpy and then how understanding changes in internal energy and changes in enthalpy can lead us to the expression relating the constant pressure heat capacity and the constant volume heat capacity for some general gas or liquid or solid. Right, and then on Friday, we'll just have that day as kind of a review day for the exam. Okay. I think that's it for kind of general announcements. Any people have questions, either about some of the announcements or questions about problems or topics in the class, things like that?
Question about question 2 on the quiz.
Okay.
It asked for the change in temperature. So I calculated the final, which my final that I got, it says what the correct answer is.
Okay. I will take a look at that. All right, I'll take a look at that.
Okay.
We can look at that right now. Other questions? Aren't. Okay. Right, so the first question has to do with the quiz. And all right, so let me set up here. Change. Yep. Yeah, I'm pretty sure that is exactly what happened there. Let me have a question. Sorry, I'm just kind of looking at it right now, reading it. Okay, yeah, that's for sure. Final temperature, not the change in temperature. So I will I'll have to regrade that. That's annoying. If I add an answer, it's still not going to do it. Okay. So yes, I'll just go through and fix that after class. I guess I can share. Right. And present. Right. So the question is question number 2. And here in the question says, what is the temperature change? And the answer is the final temperature, not the change in temperature. So I'll have to update that when I do it. So thank you for pointing that out. One day I'll stop making a mistake on these questions. I promise, so I take more care when I write the exam questions. These are ones I do like late at night, right before going to bed, and I just try to quickly put something down and find the answer. But the exam questions I look through more thoroughly. I answer them very detailed and things like that. So yeah, promise this doesn't happen on exams. But, all right. Any other questions? Okay. So we'll back to here. All right. All right. So first part, just talking about things is talking about exact differentials, right? Okay. And basically, exact differentials are related to functions being state functions, being path independent. If a function is path independent, then it has an exact differential. If it is path dependent, then it has an inexact differential. Okay. And kind of this definition here, del g del y of x equaling del h del x of y of this expression up here. Okay, that expression really is just saying this. If I have some function of x and y, right, for it to have an exact differential, okay, basically what has to be true, derivative y. I'm going to write things out specifically here. Is this, that the derivative with respect to y of the derivative of f with respect to x is the same thing as derivative with respect to x of derivative of f with respect to y. And basically, the order of your derivatives doesn't matter. Okay, that's what an exact differential is saying, is that the order in which you take the partial derivatives of your multivariable function is not relevant to the answer. Okay, right? And that and if a function satisfies that, then it's an exact differential. Okay, right? And so in the slide here, right, basically, right, because g of x of y here is just the derivative of f with respect to x at constant y. Okay, and h of x of y here is the derivative of y, or sorry, derivative of f with respect to y at constant x, right? Right, because that differential, right, any differential of a function, right, a differential, what it's talking about is some small change in that function, right? Well, that function depends on different variables, right? And that small change in that functional value is related to small changes in its variables times essentially the slope, right? That how the function changes with the change in that variable, right? Right, some small change in f here is related with how f changes with x times some small change in x, okay? Now, I mean, technically these are like partial derivatives or whatever, who really cares, right? Times some small change in y, x, d, right, times a change in y, right? And then so on and so forth. You add more variables or whatever, right? But like, right, it's right, some change in my function is related to some change in the variables times how the function changes with those variables, right? That's all that kind of statement is saying. That mathematical equation is just saying, hey, my function changes when I change the variables, and how it changes is based off the slope, right? The slope being that relationship, right, between the change in the function and the change in your variable. Okay. Right. This being true is very useful. We'll talk about it later when we talk about Gibbs free energy, after we talk about entropy. We'll use this relationship a little bit more in talking about the Gibbs relation? No. Maxwell's relations. There we go. But not to be confused with Maxwell's equations in E&M, but I believe it's called Maxwell's relationship or something like that. Okay, which relates the derivatives of certain variables with respect to other ones that we might not normally know. And we'll get to that later, but this property can be very useful, and I'll mention kind of a little bit about it again later, about the fact that our function, or internal energy and enthalpy and things like that are state functions, and so they satisfy this relationship of an exact differential. Okay, right? And so for this example here, right, looking at the differential f, right, is just df dx times dx plus df dy times dy, right? Which take the derivative with respect to x, you get 2axy. Derivative of this respect to y, you get ax squared. Okay. And then to show if it has an exact differential, you look at the derivative of this with respect to y, and the derivative of this with respect to x, okay, which both give you 2ax, right? So this is an exact. This function has an exact differential, so it is in fact a state. Questions? Definitions of exact differentials, state functions. All right. So let's apply this concept to our internal energy, okay? Right? And so I can think of internal energy, right, as a function of volume, temperature, and number of moles, right? So we talked about how, right, the internal energy changes with temperature, right? That's related with the heat capacity and such, okay? Right? Right, that internal energy change being equal to the heat transfer at constant volume is because the volume's been held constant, right? So it should kind of make some sense that there might be some other change in internal energy related if we let the volume change, okay? Right? And then there's potentially a change in your internal energy when you change the number of moles, but we're not going to worry about that until we get to Gibbs free energy and eventually potential. Okay, so for now we're still considering the number of moles as just being constant. Okay, so there's no change in number of moles. Okay, but we'll bring this back up again later. Okay. So if we just mainly think of it as a function of volume and temperature, right? And some change in internal energy is just related with how the internal energy changes with temperature times some change in temperature plus how the internal energy changes with volume times some change in volume, right? Same type of relationship we've come up with before, okay? But we know, or we have a different name for what these derivatives are, what these slopes are, okay? I guess, okay, I'm jumping ahead of myself here. Right, yeah, so it's just summing up what we've been talking about, right? This change in temperatures corresponds to change in internal energy based off of this proportionality constant, if you want to think of it like that, right? is just your slope, right? Partial derivatives. Okay. But yeah, so this change in internal energy, right, related to change in temperature and volume with these partial derivatives, right? And we have talked about before kind of what these partial derivatives are related to, one more than the other, right? Right, talked about the heat capacity at constant volume, which is equal to that slope, right? How the change in internal energy depends on a change in temperature under constant volume conditions, right? That is the definition of CV, okay? And then we mentioned back all right. Yeah, sorry. Thank you. Someone pointed that out here in class. Sorry, I didn't see that. 11:15. Okay, so it's just a minute. Okay. Crap. I hate that it does that. Right. So just kind of. Okay. So right again, this internal energy is related with change in internal energy is related with the change in temperature, change in volume, right? How they're related is through these partial derivatives, which we've talked about and shown are the heat capacity at constant volume with respect to change in temperature, right? And that change in volume is related with a change in internal energy, change in volume, right? This internal pressure, pi sub 2 is getting called internal pressure, okay? Right, and so what I was mentioning while I was muted, I believe, right, is again, having us think about how internal energy is, right, our kinetic energy plus our potential energy, right? And our kinetic energy is related with temperature. Okay, we kind of talked briefly about that relationship when we talked about Boltzmann statistics, right? And how, right, our average velocity, right, our average kinetic energy is related with the temperature of your gas, okay? Right, and so it kind of makes sense, right, that how that change in internal energy has some dependence upon temperature due to the kinetic energy of your gas, right? Well, right, for a real gas, it not only has kinetic energy, but has potential energy, right? It has these intermolecular forces, these attractive forces between atoms and molecules, right? And so, right, when you change the volume of your gas, what that's doing is it's changing the potential energy in that gas, okay? And we'll talk about that on a little slide in a minute, right? But so that internal pressure is sort of related with how the potential energy part of your gas is changing, let's say a change in volume under constant temperature conditions, right? While CV is how kind of the kinetic energy changes, okay? Right, and then we'll see, right, and we'll talk about, and we'll see, right, why for an ideal gas this term is 0, and then this term is the only thing that matters for an ideal gas, which doesn't have any intermolecular interactions. Okay? So yeah, so our change in internal energy is related with CV dt plus I sub t dv. Okay, right, and pi sub t, this internal pressure is a measure of the strength of the attractive forces. Right. Let's see here, do I have, shoot, I had a graph. I guess I didn't put that in this slide. All right, so let me screen here. All right, so if we think about some real gas, right, that has some sort of potential energy looks like this, okay? Right, this is its potential energy, right? The energy of that gas, its internal energy, function of the separation distance, right? R here, right? Of your gas, okay? Right, and so if I'm at a certain volume, right, my gas molecules on average are a certain distance away from each other, right? Right, if you were to average out as they're moving around, right, how close they are to each other at a given period of time, right? So just average over time their separation distance, right? You'll get some value, right? And let's say that value is here, right? Let's say this is my average distance between my gas molecules at volume 1, right? Well, if I increase the volume, that is going to increase the average distance between your gas particles, right? Because there's now more space. So on average, they're spending less time near each other, right? So their average distance from each other is increased, right? Well, that increase in average distance causes an increase in my energy, right? My internal energy, my internal energy, my potential energy. There you go. That's what I was looking for, right? And so, and that's what this pi sub t, this internal pressure, is measuring, is essentially how, right, a change in volume is affecting your change in potential energy and change in internal energy, and it's related with the fact that there are intermolecular forces for your gas, right? And if I'm in some attractive region for these intermolecular forces, right, an increase in volume will increase my internal energy. So let's say instead I'm out here, right, at like V2, where this is now my average separation distance, right? Now, if I increase, say, my volume, that's going to decrease, right, the potential energy, okay? Right, and so how the sign of this internal pressure, right, being whether it's corresponding to an increase in volume gives us an increase in energy, or an increase in volume gives us a decrease in energy, depends on whether or not I have repulsive forces dominating or attractive forces, right? If I have attractive forces dominating, then an increase in volume corresponds to an increase in that potential energy, okay? Some loss of internal energy, right? It's going to require some energy for your molecules to go from this point to out to here, right? So I'm losing some amount of potential energy, right? My internal energy is being decreased, right, as I'm doing this, while I gain some potential energy when repulsive forces are dominant, okay? So I just want to kind of show that figure to help kind of make sense of kind of the slide here, right? Again, of the fact that, right, pi of t is this change in internal energy with the change in volume, right? So if volume increases, right, delta V is greater than 0, right? And then pi sub t is greater than 0. That means my change in internal energy is also a positive, okay? That means attractive forces must be overcome for the expansion to take place, right? Right, so if pi sub t is greater than 0, that's meaning du is greater than 0 because we're saying dv is greater than 0, right? So everything's positive, okay? And that is in your region of your potential energy, if you will, for these intermolecular forces, when attractive forces are more dominant, right? Because we're having to overcome those attractive forces, right? In order to break these things apart, okay? And then similarly, right, then if u decreases with increase in delta V, right, that means du or delta u is negative, so pi sub t is negative, and that occurs when repulsive forces are dominating, okay? And then, right, pi sub t being 0 for an ideal gas is just for the fact that there are no intermolecular interactions, right? So there's no change in my potential energy with a change in volume, with a change in separation distance. They don't interact with each other, right? And so that's why an ideal gas only has a kinetic energy to it, only depends on that heat capacity and change in temperature, okay? But a real gas will also depend on this change in internal energy or change in internal pressure, right? And that's related with, again, the attractive versus repulsive forces in your gas. And will depend, right? Pi sub t is not going to be necessarily a constant with volume, right? Slash pressure. Just like CV, right, technically isn't constant with temperature. Now, we assume often the heat capacity is constant with temperature, but it's not always, right? And so the same thing is with your internal pressure, right? The internal pressure is not always constant with the volume, but typically we just assume it is, okay? Whatever volume range we're thinking, we assume pi sub t is constant. Right. Okay. So just before that, so any questions about kind of this differential of internal energy and this internal pressure? All right. So which, oh, 4. Need to click. No, okay. Following 3. What happened to the 4th there? Ah, well, there you go. Oh well, I know. Yeah. 3.
Can you do the exam like that?
Yeah. So for those who are hearing this on Zoom, I don't think you saw it because I didn't switch screen, but I was making edits to the slide and I forgot to freeze the screen here in class. So then everyone saw the answer that was posted on the slide. So yeah. But all right. Right? So if we want to know if these things were exact differentials, okay, we want to know, for example, is the derivative of 2 with respect to y equal to the derivative of 3 with respect to x? And they are, because both those equal 0. So A here is an exact differential, okay? Then I want to know is 6xy squared the derivative of that, right, with respect to y equal to the derivative of 6x squared y with respect to x. And it is. Those both equal 12xy if you do the math. And then finally, right, is 2x e to the minus y, the derivative of that with respect to y, equal to negative 2x squared e to the minus 2y when you take the derivative of that with respect to x, right? And here you get negative 4x e to the minus 2y, and here you'll get negative 4x e to the minus 2y. Those equal each other. So all 3 of these things, right, are exact differentials. Okay. Questions about how I did that? I know I didn't write it down. I just kind of verbally stated these things. But
For C, we always normally add them, so we assume that they're going to get to out of the
yeah. If there's a minus in these things, then it's part of sort of the like h of x or g of x. Because yeah, by default, right, that this change in f is, you know, dx plus dy plus dz plus blah, 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 blah. Yeah, so if there's a negative here, that negative is because this term itself is negative, and not that the formula itself has a defaulted negative in there. So, good question. Any other questions? All right. So, we have here ammonia, right? NH3 at 1 bar. Internal pressure is 840 pascals. Okay. CV is 27.32 joules per Kelvin mole. Question is, what is the molar internal energy change when ammonia is heated, right, through a temperature change of 2 Kelvin and compressed through a volume change of 10 centimeters cubed, right? Mm. Oh, actually. Yep. We don't need any, it's asking for the molar volume change. I mean, yeah, just, CV. Right, so I guess I think in the previous slides, right, I mean, I had the, like, CV DT and, like, yeah, yeah, you just use, like, CV DT or whatever, right? So, yeah, so, no, you don't need N here. Oh, yeah, but you're saying, right? No, you're told. Oh, but it's CVM is per mole. Okay, I see the confusion. Why that? All right. Yeah. So that should be CV comma M. I don't know. Oh yeah, no, it's CVM. Oh yeah. Right. Sorry. Okay. Now I've got myself. All right. So the question is, do we need N and things like that? And the reason why you don't need N is because we're looking for delta UM, the molar internal energy change, which is delta U divided by N. And so your N CVM, say delta T, you divide that by N, the N's would cancel. And yeah. Sorry. Yeah, I was, for some reason in the problem, I thought CV was given and not CVM. And so it's like, oh, you just use CV. And I guess because of how I've written this, it should be like pi sub t should be 840 pascals per mole. That should be, I want units to kind of work here. They're changing the locks on the doors. Yeah. All right. So how should we go about trying to find this molar internal energy change? How can we go about trying to find the molar internal energy change? What type of relationships or equations or things like that might we try to use?
You integrate it?
Yeah, yeah. So I can, right, all right, let's go, they're all good answers here, right? So I can start if I want from du equals cv dt plus pi sub t dv, right? And I can integrate that to get this expression here, okay? Right, and if you're not comfortable doing, say, that integration, right, just by saying, oh yeah, I would just like kind of integrate over t and v or something like that, right? Think of it this way. Think of, right, what I could also think of how I would do this problem is I could say delta u total is equal to delta u1 plus delta u2, right? Internal energy is a state function, right? So how I do my change doesn't matter, right? So I could think of, in step one, doing a constant volume process where delta u1 is just cv delta t, right? And then for step two, I do a constant temperature process where delta u2 would then be pi sub t delta v, right? Okay, and I'd add those together to get delta u total, which is the same as this guy up here, right? And so, right, we can, and again, we can do that because u is a state function, so I could break up this change. Instead of thinking of it happening all at once, I could think of it happening sequentially, right? And then, right, and then, and then if we're more comfortable thinking about, what is delta U for a constant volume process and what is delta U for a constant temperature process, we would get those two equations, right? And then add up those two changes in internal energy, get the total change in internal energy. Okay? So any questions about why we're using this expression here? All right. And so basically, I just need to be kind of plugging in for things, right? Delta T is 2 Kelvin. My pi sub T, 840 pascals per mole, right? My CV, 27.32 joules per Kelvin mole, right? My change in volume, I could do a number of ways. So originally, I was like thinking, okay, well, in liters, it's 0.1 liters, okay? But since this internal pressure is given in pascals, if I get my change in volume in terms of meters cubed, meters cubed times Pascal is equal to joules. So then I don't need to convert between like liters, atmospheres, and joules and things like that, right? Because otherwise I'd have to convert pascals to atmospheres. Then I'd convert my liters, atmospheres to joules, and kind of pointless. Now you'll see that's what I ended up doing in the slides, but you get the same answer leaving it like this, right? So now all I just got to do, right, is delta U is equal to 27.32 times change in temperature, which is 2, plus 840 times change in volume, which is 0.0001. Okay. So this delta U, huh? Oh, yeah, I was about to look that up because I had forgotten what it said. Okay, so it's compressed and heated. Yeah, okay, so it should be negative. Thank you. Delta V is a negative value. I'll swap back to paper here. Yeah, that's what I was about to check myself is whether or not I had the signs correctly. I'd forgotten to make a note to myself when writing down the numbers here. So, right? Yeah, so this is a negative, right? Because my change in volume is negative, right? Because it's being compressed. Okay. Right, and so we kind of break up these things, right? 27.32 times 2. So this is 54.64 joules per mole. Okay, I haven't written down the units here, but the units you'll get joules per mole. And then this will be minus 0.084 joules per mole. All right. So delta U is 54.56, roughly rounding, joules per mole. Yeah. That is the change in internal energy, right? The molar change. I should have molar here, but these are all molar values. Okay. Yeah, so that's a molar change in internal energy for this process, right? Again, I just calculate from that equation top here, right? And we use the fact, right? Again, you can easily use the fact and the idea of delta U being a state function and thinking of calculating it in terms of two changes in internal energy for two different processes, one at a constant volume and one at a constant temperature. Okay. Questions?
So Pascal is just meters.
Pascals would be, well, joules is pascals meters cubed. So Pascal is like a joule per meter cubed. Right? Because Pascal is force per area. Force times distance is work or energy. So right, Newton meter is joules, and then area times meters like a volume, right? So then you get joules per volume. So. Other questions? All right. Right. So how I did the switch on the slides here is I actually did convert to liters and then atmospheres and then back to joules, right? But you see, right, I basically have to divide by like 101.325 and then multiply by 101.325, right? Like I'm basically dividing and multiplying by the exact same number because I convert, back away from SI units to SI units, which is kind of pointless. I also made a typo there. It should be 840 divided by 101. Oh, no. It's 84. Yeah, sorry. Because I have 840 times 0.1. No, so there was no typo there. But yeah. But again, I just wanted to leave this here as just a reminder that, again, you can go different ways to find the same answer, and that's fine, right? If you are more comfortable in expressing your pressures and atmospheres and did that, which is what I originally did when doing this problem, right, of converting pascals to atmospheres, and then later on converting your liters, atmospheres to joules, you get the exact same answer as just using pascals and meters cubed from the beginning. Okay. All right. So it's actually kind of a shorter stuff for the day today. Again, I'm trying not to kind of rush us, and also because of how things are being done this semester. Some days will be like this, where there's less kind of examples and things like that to go over with the topic, since more time of the day would have been spent on discussions and lecturing rather than working through problems. So, but yeah, there's not very many other problems we can do besides just change the numbers in this problem, right? With talking about pi sub t, right? Now I could ask, right? So we'll just ask a quick conceptual question here, right? As a reminder, right? If I have a gas with a compression factor Z less than 1, will the change in internal energy be positive or negative with a positive change in volume? So, right, let me.
Wouldn't it increase internal energy?
So right, increase is what here. I'm just gonna kind of write out the question to make sure, right? So Z is less than 1 for your gas, right? What is delta U? Is it, less than 0 or greater than 0, right? When delta V is greater than 0. Okay. And so we have one person saying greater than 0. People agree with that or disagree with that. See, at least a nod, agreeing, right? Right, and it is delta U will be greater than 0. Pi sub t is also going to be greater than 0, right? Because when Z is less than 1, that means attractive forces are dominating, right? Right, the most important, not domination, dominating, right? The most important intermolecular interactions when Z is less than 1 are the attractive ones, okay? And so when attractive forces are dominating, right, as you increase your volume, you're having to overcome these attractive forces, your internal energy is going to increase as well. And that's going to have a positive value for pi sub t, okay? Well, what now? So yeah, Z less than 1 will have a pi sub t greater than 0, and Z greater than 1 will have a pi sub t less than 0. Yeah. Yeah, exactly. Yeah. If you had like some sort of a plot of Z pi sub t, right, and here's 1, right? So it'd be 1 at 0, and Z equals 1, pi sub t is 0, and then when Z is less than 1, pi sub t is, Z is greater than 1, okay, pi sub t greater than 0 means that Z is less than 1, so it'd be like this, right? Some sort of like line sort of like that, right? Right. I guess Z wouldn't quite look like this because Z is never going to be less than 0, right? Be something like this or whatever, who knows? But right, some type of thing, right? Yep. So there's a question here on Zoom. Are we going to have test review or example tests? So I don't have example tests for you. Your example tests are the homework questions and the questions we do in class. Those are literally the exact same type of questions that are on exams, okay? Right? There are no new sets of equations or formulas or things like that, right? So the questions you see on homeworks and in class are the same type of questions you would see on an exam. And in terms of review, yes, we will have a review on Friday for the exam. Right, tomorrow we're going to talk about relationship, or not tomorrow, Wednesday we'll talk about relationships between CP and CB, which I will post that video sometime today, kind of the lecture video portion of that lecture on YouTube sometime today. I forgot to do that over the weekend, so I'll post that for those who want to view it before class, which again, I highly recommend you do view these videos before class, before coming. I post. I don't make them for myself. Okay. And then, oh yeah, you're right. The like participation quiz questions as well are good places to kind of just review. Some of those do have, you know, some numerical answer type things you have to do, but also have some conceptual things that help, right? Make sure, you know, we understand what's happening in the problem and things like that, right? So yeah, so the quiz questions, the participation quiz questions are also a good place to go as well. But yeah. Okay. And if you want further examples, like I said, there are the questions in the extra notes, I think is what it's called, on Canvas, right? That were created by a previous faculty member here, right? And so I recommend glancing over those as well if you want extra problems to do, new problems to do. They do have solutions at the bottom of those extra notes and things like that. And the topic numbers are related with the topics numbers that we have in the class. Okay? So other questions people have for the day today? If you turned in your homework and haven't picked it up yet, I do have it here with me, so you can always pick it up today. And I'll try to remember to bring it for the rest of this week. But yeah. If there are no other questions, and we'll end up ending a little earlier today. Okay. I'll wait a second to close out Zoom. Okay, so yeah. So Samantha, go ahead with your question. You can either type it out or say it, whatever you feel like.
I had a question about number 2 on the participation quiz we just took over enthalpy and adiabatic changes.
Yeah. So that was at the very beginning of the class. That was also kind of brought up. Yeah, I accidentally put the answer there as the final temperature, not the change. I'll fix that and update that today. So yeah, so that was my fault. Yeah.
Okay, thank you.
Yeah, thank you. All right. End this meeting now.